Hello class, we're going to go over the molecular mechanism of synaptic, vesicular, exocytosis. So we're going to learn about how synaptic vesicles in the presynaptic neuron, how they fuse with the membrane and release their neurotransmitters into the synaptic cleft. And we're going to talk about a very special class of proteins, not exclusively, but some of the big ones we'll talk about today are what's known as snare proteins. In class, we went over the very long sort of explanation of what this acronym stands for, and it stands for the soluble N-ethylmalinide sensitive factor attachment protein receptor. And you don't need to know that, you just need to know that these are called snare proteins. Not SNAP, but snare proteins. And so what do all of our snare proteins have in common? Well, they have what's known as a snare motif. And a snare motif is a long alpha helix structure. Let me get one that works. In the proteins. We talked about this in class 2. This is a secondary structural characteristic of many proteins. And all of our snare proteins have this very long alpha helix structure. All right, so this is our alpha helix. And there are 4 different kinds in our snare proteins that we want to know. Are QA, QB, QC, and R. 4 distinct types of snare motifs. And as I also mentioned in class, one of the functional significance of these is the fact that they do what's called zippering. So I'm drawing one snare motif here. That's sort of, you can think of it as being, the whole thing is kind of spring-shaped, but that spring itself is becoming somewhat spring-shaped too. You can imagine taking a spring and bending it like a corkscrew. And in this conformation, another alpha helix, another snare motif, can kind of intertwine with these. And this is a lower energy state conformation. So it doesn't take any energy for this to form. For the snare motifs to be straight and unbound, this is actually a higher energy state. And so when this zippering occurs, it releases energy. And this is at the heart of fusing the vesicles to the presynaptic membrane. So let's introduce our very first snare protein. Okay, so our first snare protein that we're going to talk about is one of 2 snare proteins that are subclassified as little t, snare proteins. And the first one we're going to talk about is called syntaxin 1. Syntaxin 1. All right, so I'm going to first draw our lipid bilayer. This right here represents our presynaptic neuron. we're in the axon terminal here. Right, and this is the intracellular space. So this is our cytoplasm. So I'll just write that up here as a reminder. And down here, this is our extracellular space, and this is going to be the active zone, right, of the presynaptic neuron, and so this must be our synaptic cleft. Okay, so syntaxin 1. Let me get my colors here arranged. We'll use blue and red. So our protein is a transmembrane protein, so it spans both the intracellular space and the extracellular space. All right, so it goes through our membrane. And there's a little intermembrane alpha helix here. And I'm going to first draw the protein sort of bent on the side here, but you can think of this protein as being a structure that is kind of flexible and can kind of float around in the cytoplasm. And syntaxin 1 has our alpha helix snare motif. And so I'll draw all of our snare motifs in blue. And the protein goes along, and it also has this other interesting structure here, also constructed of an alpha helix that's folded in on itself 3 times, like that. This little bit here, the triple alpha helix, is called the capital H A B C domain, and we'll see its functional significance shortly. Now our membrane, or not our membrane, our protein here, to orient you the 2 different sides here, this is our C terminus. So this is the end of the protein that has the carboxyl group, and then this must be our N terminal end, which has the amino group on the end. And so the important thing to realize here is that all the alpha helixes, when they go through that zippering process where they intertwine with another one, this is something that starts at the N terminal, or the terminal N side of the alpha helix, and zips down towards the C terminal. So it goes from N to C as it goes down. Okay. Now, this is what I've drawn here is what we would call the open conformation of syntaxin 1. And what makes it open is that this alpha helix motif, this snare motif here, is free. It's not bound up with anything else at the moment. But it does exist in a closed version. And so let me draw that for you. I'll just draw it down here at the bottom. So I'm going to draw a little dotted line here so that we don't get confused about where the protein is. It's not going to be in the synaptic cleft. So this is just a whole nother page down here. This isn't necessarily below our synaptic cleft. So here is our membrane again, our phospholipid bilayer. And I'm going to this time draw our protein in a different conformation to highlight how flexible this part of the protein is, and that it's just sort of kind of is able to kind of float around here in the cytoplasm. You can think of it as like seagrass kind of. So there's our alpha helix in the membrane, our C terminus, and I'm just going to draw this protein just straight up. So here's our snare motif. And now, instead of an open conformation, it's going to be in a closed conformation. And it's closed because this HABC domain is now folded back and is now interacting with the snare motif. So it's actually bound right here where I draw this black squiggly line that just indicates that these are interacting with each other. And so this is what we call the closed conformation. Right? And conformation is just a word that we use to denote the specific shape of the protein. So you can have the same protein that exists in multiple different forms, multiple different conformations. So this is the closed one. So this snare motif is inaccessible. So no other snare motif can come in zipper with this because the HABC domain is in the way. Okay, so here we are taking a look once again at Syntaxin 1. And what conformation is it in? You can see that the HABC domain is interacting, is on top of the first part of the snare motif, and so this makes it the closed conformation. Okay, so there's another protein that comes along that we're interested in. It's not a snare motif, not a snare protein, but it's very important for this process of vesicular exocytosis. And it's called MUNC18. And it binds up here to the HABC domain in the N-terminal part of the snare motif, MUNC18. And this sort of keeps it in this closed conformation. So right now, this protein is relatively inert in that it can't zipper with any other snare motifs because it's bound up with the HABC domain. And also that is bound up with MUNC18. Now in our active zone, here we have another protein, another snare protein, alongside Syntaxin 1. And it is SNAP25. SNAP25. And this structure is quite a bit different, though it does still have, because it's a snare protein, right? Both of these are snare proteins. In fact, both of these are T snare proteins. Well, we can make it blue. And I don't think I wrote this at the beginning. But what does the T stand for? The T stands for target. So these are the target areas in the presynaptic active zone that the vesicles will eventually dock at and bind to. Right. So this is the target for the vesicles. Now, SNAP25 has a different structure. It's not a it's not a protein that spans the entire membrane. In fact, it doesn't even, the protein itself doesn't go into the membrane. So the protein itself connects to these lipid molecules that are normal constituents of the membrane. And SNAP25 has two snare motifs. So you can think of it as this U-shaped protein, and its two ends have alpha helixes that potentially could zipper with others. But not so in this state right now, because, or SNAP25 could not zipper with syntaxin 1, because syntaxin 1 is bound up right now with HABC and MUNC18. And before I talked about the specific names for the motifs, and here we have our first three. Syntaxin 1 is our QA motif, and then the N-terminal portion of SNAP25 is QB, and then QC, our third one, the C-terminal end of our SNAP25 protein. Now there's one more protein that we're interested in at this point, and it is MUNC13. So can you take a guess at what protein it's going to interact with? It is going to come along here and interact with MUNC18. And so what does it do when it does that? It binds to MUNC18, which allows it, which facilitates a conformation change in syntaxin 1. So MUNC18 plus MUNC13 gives us the open conformation of syntaxin 1. So now what can happen is our alpha helixes, our snare motifs, can now zipper with each other now that syntaxin 1 is free. And that's exactly what they do. These three motifs here zipper together. And remember, this doesn't take any extra energy to do that. They're in a higher energy state unzippered, and so zippering actually produces energy. Right? There's a lot of potential energy bound up in these unzippered snare motifs right now. Now I want to introduce not the last protein, but the last snare protein that is of importance for our synaptic vesicular exocytosis. And this one is not in the presynaptic membrane protein, the presynaptic membrane of the active zone, but rather it's in the vesicles. And remember, our vesicles are spherical, membrane-bound organelles. So they have a phospholipid bilayer, just like the membrane down here. It's functionally the same thing. They have a different sort of motif of various proteins. There's lots of proteins. But it's the same stuff. It's a lipid bilayer. And so the protein in here that's of importance. Oops. I forgot to draw the ever important snare motif. So this protein is called synaptobrevin. The C terminus is on the inside of the vesicle, and the N terminus on the outside in the intracellular space of the presynaptic neuron. And I should write synaptobrevin. Synaptobrevin this alpha helix snare motif is our fourth one, and it's called R. And so synaptobrevin is going to be able to zipper with this complex with the other three motifs. And collectively, we call this complex a 4 alpha helix bundle when they're all zippered together. All right, not a very fancy name, just a descriptive name. Okay, so let's take a look at this right here. We'll get oriented. Things look a little bit different than they just did on the last slide. So we have, this looks familiar here. Yes, we have 4 different snare motifs here. And I'm not showing it because I think it would just get too messy. But they would start zippering here, right? And so remember what this was called. This is our 4 alpha helix complex. And we have all 4 here, which includes, I'm going to start from the bottom, 2 of our T snares, 2 of our T snare proteins. So our first one, syntaxin 1, which is bound to the membrane, the presynaptic neuron membrane at the active zone. Our second protein, which is bound to the membrane via these lipid molecules, is our U shape, and it has our 2 middle, as they're pictured here, our 2 middle snare motifs. Do you remember that one? SNAP25. And then we have our third snare protein, which is giving us our 4th snare motif, our 4th alpha helix that's going to zipper here. And this one is what we call a V snare, so another subclass of snares. And this one, as I mentioned before, is synaptobrevin. And any idea what the V stands for? All right, vesicle or vesicular. So we have our target snares and our vesicular snares, or vesicular. Okay, so in this conformation here, you can see how easily now these vesicles can be brought down towards the target zone and to the target snares in the active zone of our presynaptic neuron. All right, getting close here to merge. And as they get in this conformation here, they will start to zipper. And they zipper from sort of from furthest away from the vesicle towards the vesicle. But they don't go all the way. There's another protein in here that we call complexin, which I'm just going to draw as a simple line right here. Complexin interferes with the zippering process. So we can't zipper all the way, even though it wants to. Remember, there's a lot of potential energy in these alpha motifs, and they want to zipper together. But they can only go one way, just like the zipper on your jacket. So it can't produce exocytosis, not yet at least. Not without the help of yet another protein, synaptotagmin, which is in the vesicle. This is a protein that does not have a snare motif. So it's not a snare protein. But it is important for synaptic vesicular exocytosis. Okay, synaptotagmin. Now let's talk about this in more detail. Synaptotagmin and what it does. All right, so I've kind of cleared things away here. So we have our membrane here, presynaptic membrane. Right here in our intracellular space in the axon terminal, we have a vesicle. Remember, these vesicles are filled with neurotransmitters that are eventually going to be released into the extracellular space, released into the synaptic cleft. But let's talk about synaptotagmin. And I'll write that up here again, just so it's always here. Right, so there's these two structures here that are the most important to consider for this process. And it is, or they are called the C2A and C2B domains of the protein. And our N-terminus inside the vesicle, and our C is in the intracellular space in the cytoplasm. Now, what's interesting about these domains, C2A and C2B, they have a strong affinity for calcium ions. C2A attracts 2 calcium ions, and C2B attracts and binds 3. So they're able to bind a net of 5 calcium ions. And remember, calcium has a +2 charge. And so there's a lot of positive charge in the synaptotagmin when there's calcium available to bind. And so there's a net of a +10 charge in the synaptotagmin. I'm going to take a close look at these structures here. We've talked a lot about alpha helixes, but the other common secondary structure in proteins are beta sheets. And these beta sheets, let me just draw, I'm drawing sort of just this two-dimensional plane here. We'll use red. And we'll use brown for the beta sheets here, since we haven't used brown yet. Right, and so these beta sheets are made up of a string of amino acids that kind of bend back on each other and form bonds with each other. And so you can kind of think of it now, I'm sort of drawing the lines of what would be the individual proteins. All right, and right here we have 2 beta sheets that are stacked on top of each other, right? But they're part of the same protein, right? And so you can see it's a continuous, this amino acid sort of here it's leaving the beta sheet, so it no longer has amino acids here that are part of the beta sheet, and then it starts a string of amino acids that can form a secondary structure of a beta sheet. So we have two sheets in parallel here, right? 2 beta sheets that kind of sit on top of each other, and they make a sandwich, and that's what this is called. We call this these structures here beta sandwich. And so synaptotagmin has two beta sandwiches. There's one here and one here. Two different beta sandwiches. So these blocks right here each represent two beta sheets that are stacked on top of each other. And it's in here that in these loops of the beta sheets of the beta sandwich that binds our calcium ions, right? And this beta sandwich binds 2 calcium ions, and this beta sandwich binds 3 calcium ions. Now, what's the functional significance of our synaptotagmin having all of this excess positive charge? Well, think about what's happening in the axon terminal during when an action potential enters, right? Because this is the only thing that is going to, that would naturally invoke a huge surge of calcium ions. So synaptotagmin isn't going to suck up calcium ions in the beta sandwiches unless there's a lot of calcium in the axon terminal. And that only happens when an action potential enters. So an action potential is fired in the neuron, it reaches the axon terminal, and we know that this stimulates membrane, the change in the membrane potential activates these voltage-gated sodium channels. I'm sorry, the voltage-gated calcium channels, and calcium floods in. So what's the electrostatic environment of the axon terminal of the presynaptic cytoplasm? It's really positive because of all this calcium that's flooded in. Right? And so the synaptotagmin is filled with a +10 charge per protein, and there's 2 of them in our sort of the way we've drawn things here. There would be 2. You can kind of think of it as like 1 per 4 alpha helix complex with all those alpha helix motifs. Right? So this in reality there's more than 2. This is a 3-dimensional structure, so there's actually more than 2 of the 4 alpha helix complexes that are all around. There could be 3, 4, 5, a lot more. And it's the same thing for synaptotagmin, but for each synaptotagmin, a +10 charge, it's going to be drawn to electrostatically to the relative negative charge of the extracellular space. So there is this electrostatic draw. Now there's something else here as well besides just this electrostatic charge, but the C2b sandwich here can bind to a structure in the postsynaptic membrane that's called PIP2. Now, PIP2 is a phospholipid. It's not a protein. But it's a natural constituent of the presynaptic membrane. And so it can bind to C2b. So it has this electrostatic force that's bringing it down. C2b can bind to this PIP2 phospholipid. And so this is bringing the vesicle down towards the membrane. And so let me switch back to our larger complex here. C2A, C2B, and with all the calcium around, this is filled up with its calcium ions, which draws it down towards the membrane, C2b is attracted to PIP2, which is in the membrane. So those two elements are bringing synaptotagmin down, which is facilitating the docking and the eventual merger of the synapse with the membrane. With the vesicle with the membrane, which will open it into the synapse. And there's one more thing, in perhaps the most important aspect of this mechanism, is that synaptotagmin, it also interacts with complexin. And basically what it does is it frees up our alpha helix snare motifs so that they can fully zipper together. And remember, this is a very energetic process. This full zippering releases a lot of energy. And so all of this combined, the zippering and synaptotagmin facilitating that, and also itself being drawn down to the membrane, moves this whole vesicle complex down towards the membrane, closer and closer, and all of that force literally squeezes it down to the membrane. Now, let's take a quick look at just what that, the actual moment of exocytosis looks like. All right, so I'm going to go over the dynamics of the vesicle actually fusing with the plasma membrane. And so we have our vesicle here, and remember it's composed of a lipid bilayer, so that's why I'm drawing two layers. And this is the plasma membrane of our presynaptic neuron. And we have our snares and synaptotagmin that are working right here. I'm not going to draw them, we just looked at that, and they're squeezing down the vesicle towards us. So what does it look like right here once it sort of squeezes down and it actually starts to make physical contact, these two membranes with each other? Well, initially we have something that we call a fusion stalk that forms. And that's right here. The fusion stalk. And I'm going to draw some of the little hydrophobic tails of the plasma membrane to give you a better idea of what's going on. If you remember, our lipid bilayer is composed of phospholipids, which are amphimixous. They have a positive polar side, which orients towards the aqueous solution, because water is also polar. And so they're attracted towards each other. The positive charge of the phosphor group and the negative side of water. And the hydrophobic tails of the phospholipid orient towards each other. Right? So they're still kind of protected from the water here because they're still oriented towards each other. So that's our fusion stalk. And so as this gets pushed down, you can imagine this stalk getting wider and wider. And it looks a little bit something like this as it goes along. I'm not going to draw the whole vesicle. And at this stage, when this stalk, this fusion stalk expands, and we have this sort of, we just call it hemifusion. So it's sort of like a half fusion of the vesicle membrane and the plasma membrane of the presynaptic neuron at the active zone. And so you can see it's not a full fusion yet. All right, we still have our neurotransmitters are still bound in here. There's no direct communication between the lumen of the the vesicular space and the synaptic cleft. They're still in there. And so the only thing that needs to happen now is the beginning, as force is still bringing this vesicle down into the membrane and squishing them together, is a little hole to open up somewhere here to make that initial breach. Until it looks something like this. Let me make sure that I get this right here. My three-dimensional, my brain here is sort of lacking in its three-dimensional ability. So let me draw it this way first, and then we'll just erase in a hole there, and I think that'll ensure that I get this right. Yes. And so we're just waiting for a little pore to open up in our hemifused vesicle and membrane like this. And these hydrophobic tails, they don't want to be exposed. You're never going to get these things sort of open to the water because they just automatically will orient towards each other, right? Sort of being driven by that electrostatic force of the polar regions, right? And so this is what the membrane looks like here, like that. So the hydrophobic tails are always oriented away from the water. And so now we have this initial breach. And neurotransmitters can now leave. They can start to leave because we have this open communication between the lumen of the vesicle. All right, now this is our vesicle. I'll draw it completely here. All right, so now this little pore opens, and this is called a fusion pore. And it just grows and gets bigger, and you end up with something that starts to look like this. I'm going to draw it a little bit smaller now. So we'll make that inside there. And more neurotransmitter can come out, and it really starts to flood here as there becomes less of a distinction between the inside of the vesicle and the outside of the axon terminal in the synaptic cleft. And so at this point, we have full fusion. And this continues until eventually this distinction of the vesicle becomes less and less, and it becomes fully integrated into the plasma membrane of that presynaptic neuron at the active zone. And that's what that fusion dynamic looks like, all driven by our 3 snare proteins, or 2 T snare proteins, right, which you should make sure that you know very well. Syntaxin 1 and SNAP25, our V snare, synaptobrevin, and then our 4th important protein that is not a snare, but still is very important for this process, synaptotagmin. Okay, thank you for your time. I hope that was clear. Let me know if you have any questions. and I'll see you in class.